Welcome to the deep dive. Imagine trying to piece together a cosmic car crash, but instead of car parts, you've got, well, the tiniest particles in the universe.
That's a great way to put it. It's like a puzzle on the most fundamental level.
We're diving into the world of particle physics today, getting our hands dirty with quarks, gluons, and this really cool thing called unsupervised quark-gluon jet tagging.
And just to clarify, when we say unsupervised, we mean the AI is figuring things out without any pre-existing labels or instructions.
Exactly. No cheat sheet for this AI. It's learning by doing, like a detective at a crime scene with no witnesses. But before we get ahead of ourselves, let's bring in our expert who eats, sleeps, and breathes this stuff.
Happy to be here. Always love talking about this kind of research. It's like where physics meets detective work.
Okay, so let's rewind for a sec. For those of us who haven't cracked open a physics textbook lately, what exactly are quarks and gluons? Give us the Spark Notes version.
Right, so everything around us is made of atoms, yeah.
Last time I checked, yes.
So think of atoms like those tiny Lego blocks, the ones you step on and regret it instantly.
Ouch. Yeah, know those well.
Well, quarks and gluons are even tinier. They're like the bumps and connectors that hold those Lego blocks together. They're fundamental particles. Can't break them down any further.
Okay, so those are our Lego pieces.
Got it.
Now, how does the Large Hadron Collider, this massive machine we always hear about, actually help us study something so unbelievably small?
The LHC. It's basically a supersized particle accelerator smashing protons together at ridiculously high speeds, close to the speed of light.
So like a cosmic game of billiards, but with, way more energy.
Exactly. And when those protons collide, boom, they create a shower of particles, including those sneaky quarks and gluons we're trying to track. We call these showers jets.
Okay, jets, got it. So it's like a controlled demolition at the subatomic level. And by analyzing these jets, scientists can kind of reverse engineer what happened and learn about the fundamental forces at play.
Exactly. But here's where it gets tricky. We need to figure out which jet came from a quark and which came from a gluon. It's not like they come with name tags.
That's where I imagine this unsupervised quark-gluon jet tagging comes in, right?
Right.
So how in the world did researchers even begin to tackle this? What'd they focus on?
They zeroed in on this particular characteristic of jets called soft drop multiplicity, or NSD for short.
Catchy.
Right. Think of it like a fingerprint, a way to tell these particles apart.
Okay, so NSD is our fingerprint. How does that actually help differentiate quarks and gluons, though? Like, what makes their NSD unique?
So scientists, based on theoretical models, believe that the NSD values for quark jets and gluon jets follow this thing called a Poisson distribution.
Poisson distribution. Okay, gotta admit, you've lost me a little there. Hit me with an analogy, maybe.
Okay, imagine you want to know how many raindrops will hit a very specific spot on your window during a storm. A Poisson distribution helps you calculate that probability. It's basically figuring out how likely it is for a certain number of events to occur within a certain time frame or space.
Okay, that makes more sense. Raindrops, got it. So they use this Poisson distribution to try and predict the NSD values for quark and gluon jets. But here's the real kicker, right? They don't actually know which jet is which beforehand. That's what makes it unsupervised.
Nailed it. It's like trying to sort socks in the dark. You can feel them, but you can't see the colors.
Exactly. So they basically just fed a computer all this data and said, hey, figure it out. No hints, no labels, just raw data.
That's the beauty of unsupervised machine learning. The computer's job is to play a giant game of which one doesn't belong. It looks for patterns in the NSD data and separates those jets into two groups without ever being explicitly told which group is which.
That is seriously impressive. So did it work? Was the computer able to sort the jets accurately?
It did. And this is where it gets really cool. This method, just using that Poisson assumption and the NSD values, it was able to differentiate between quark jets and gluon jets with a decent level of accuracy.
Okay, hold on. Don't leave me hanging. What do we mean by decent? How accurate are we talking?
We're looking at an accuracy in the range of roughly 0.65 to 0.70.
So wait, the computer, by itself, just by looking at patterns, could tell quarks and gluons apart. That's amazing.
It is. It's like trying to identify the ingredients in a cake just by tasting it. It's not easy, but this AI is doing a pretty darn good job. And remember, this was all with simulated data, the ideal scenario. So naturally, the researchers wanted to know, could this method hold up in the messy, chaotic, real world of the Large Hadron Collider?
Right, because it's one thing to analyze a perfect simulation, but real life is messy. It's like the difference between I don't know, reading a recipe and actually trying to bake a cake with a toddler hanging off your leg.
Ah, that's a great analogy. It's definitely more like baking with a toddler, that's for sure.
So how do they even go about recreating that kind of chaos in their data?
They basically smeared the data. They introduced this artificial noise to try and mimic the messy signals that a real particle detector would have to deal with.
So they're basically roughing it up a bit, adding in some extra static, making it more realistic. So
Uh,
did it still work? Could their AI detective still crack the case with all that extra noise?
Here's the amazing part. It did. Even with all that extra complexity, the unsupervised learning method was surprisingly resilient.
No way, the accuracy stayed the same, even with the smeared data.
It remained pretty darn consistent. There were some minor shifts in the actual values the model learned, but the overall accuracy in terms of differentiating between the quark jets and the gluon jets, that was virtually unchanged.
Wow, so it's robust, this method.
Yeah.
It can handle a little real-world messiness.
Yeah, exactly. And that's super important because ultimately the goal is to be able to use this to analyze the real deal, the actual data coming out of the LHC.
Makes sense.
Yeah.
Now, you mentioned something earlier about Bayesian inference. Does that factor into all of this too?
It does. It's like giving our AI detective a whole upgrade in its toolkit.
Ooh. Okay, I'm listening. Tell me more.
So up until now, we've been talking about this method as finding the single most likely answer, right? Like this is most likely a quark jet. Bayesian inference, though, it takes a slightly different approach. It's more about figuring out the probability of different answers being correct.
So instead of just one definitive answer, it's more like a range of possibilities with probabilities attached. Like there's an 80% chance this is a quark jet, but hey, there's also a 20% chance it's something else.
Exactly. It brings in this element of like acknowledging the uncertainty that's always present in these kind of measurements.
Okay, yeah. Uncertainty, definitely a thing in particle physics, I'd imagine.
Hmm.
So how did they incorporate that Bayesian approach? How do you even build that into the model?
They used what are called priors.
Priors. Sounds kind of mysterious.
Mhm.
Like some secret knowledge passed down through generations of physicists.
Huh. Not quite, but I like the way you think. Priors are essentially a way to build in any kind of existing knowledge or assumptions you might have into the model. In this case, they actually used very general priors, like basically saying, we don't have strong opinions about the exact values, but we know they need to fall within physically reasonable limits.
So it's like setting some boundaries, making sure the model doesn't go completely off the rails. What happened when they added those priors in, though? Did it change things much?
Well, this is where it gets interesting. Even with those very basic priors, the Bayesian inference revealed something pretty cool, the predictions from the model. They line up really well with the simulated data, but it wasn't a perfect match. There were these small but important differences.
So their model, just like any model, it's still a simplification of the real world. It's not perfect.
Exactly. But think about it, even though it wasn't a completely perfect reflection of every single detail, it still managed to achieve a really high level of accuracy.
It's like, I don't know, recognizing a song, even when the radio reception is kind of fuzzy. You can still get the gist of it.
Yeah, that's a great way to put it. It shows how powerful it can be to combine those two things, the unsupervised learning with the Bayesian inference.
It's like, we're not just classifying particles here, right?
Yeah.
We're pushing the boundaries of how we even understand the universe.
Right. And get this, when they actually used that Bayesian approach to classify the jets, they got an even higher accuracy, bumped it all the way up to 71%.
71%. Wow, okay, so they really squeezed out some extra accuracy with that Bayesian magic.
Yeah, it really shows how valuable these statistical tools can be, especially when you're working with, data this complex. Particle physics, man, it really puts those tools to the test.
We're talking about some pretty big implications here, right?
Yeah.
I mean, this is just about sorting particles, is it? We're talking about quarks, gluons, the strong force, the fundamental forces that hold the universe together.
Absolutely, you're hitting the nail on the head. By understanding these particles and how they interact, we're basically lifting the veil on reality. And the fact that AI can help us do this, that we can train it to make these distinctions without telling it exactly what to look for, that's huge. It's a whole new way of doing physics.
I mean, if we can do this with quarks and gluons, what's next, right? Dark matter, the Big Bang. The possibilities are pretty mind-blowing when you think about it.
It really is exciting. And this is really just the first step. We've got this powerful new tool now, and who knows what we'll discover with it.
We've got the key, now we just got to find all the locks it opens.
Oh.
I like that.
Yeah.
Well, expert speaker, this has been an amazing deep dive. Before we wrap up, though, any final thoughts for our listeners? What's the one thing you really want them to take away from all of this?
That's a good question. I think the biggest takeaway for me is that even in particle physics, a field where things get unbelievably small and complicated, there's always more to learn. And sometimes, the most exciting discoveries happen when we kind of step back and let the data guide us, let go of our preconceived notions.
It's like that old saying, the only constant is change. Even when you're studying the most fundamental building blocks of the universe, the quest for knowledge, it never really ends, does it?
Exactly. And hey, who knows? Maybe someone listening to this right now will be the one to make the next groundbreaking discovery in particle physics.
Yeah, wouldn't that be something? That's how you untangle a jet stream, everyone. Big thanks to expert speaker for taking us on that incredible journey today. And for our listeners, as always, keep those brains buzzing because the universe is full of mysteries just waiting to be solved. This has been The Deep Dive. Until next time.